Hello, my name is Gonzalez, and today I'm going to talk briefly about one of the products that I have worked with, which is Navencrypt. As a quick search, you're going to find that Cloudera's product named Navencrypt is a transparent encryption tool to encrypt data at rest. Basically, it's going to encrypt directories, entire directories, or per file encryption. This is the basic architecture that it's working with. Basically, you have an application, and it's a user space application that is communicated with the kernel module, and the kernel module is called Navencrypt FS, and it has a hook, meaning that every single read or write of any I/O is going to be intercepted by the Navencrypt kernel module. So it sits on top of eCryptFS or DMCrypt to perform the encryption, and the Navencrypt kernel module as well does a process authentication and has a cache, which is a data structure as a list. Also has an access control rules that are gonna whitelist those processes that are allowed to access the encrypted data. So basically, it's gonna get the fingerprint of a particular process that is allowed, and if it's allowed, you can do the read or the write operation. So basically, it's a wrapper to eCryptFS and DMCrypt, and it's gonna control every single access from the user space. It works with different file systems and also works with multiple Linux versions such as SUSE, Red Hat, Debian, CentOS, Ubuntu. So it supports wide number of kernels, and that's one of the complexities of the product. I mean, itself it's a pretty clever solution, but the maintenance and the support of new versions or new releases, it's a complex challenge. So in a different view of the architecture, you can see that you're going to have an ACL rule that is going to allow a specific category. The category is the anchor that is going to match the encrypted directory with the process that is allowed. So in this case, we're allowing the process my app to access whatever is encrypted under my logs. So you can specify different mount points where the encrypted data is going to be stored, and it can be use different devices that can be virtual devices or any other type of device. And Navencrypt uses as well the key trustee, which is a Cloudera product, and it's used as a key manager to store the encryption keys. Basically, every single prepared mount point for encryption needs a key, which needs to have a key manager as the key store where the keys are going to be placed into in a secure way. And it's communicating the Navencrypt client with the key trustee server through GPG. Now it's important to know that the only open source that we have available is the kernel module. All the Navencrypt application that sits on the user space, it's CLIs with the key trustee are Cloudera's proprietary. So I'm going to be talking only about the kernel module in a quick walkthrough. Now you can contact Cloudera to get the source code of the Navencrypt kernel module, or it's also available on the OBS system of SUSE, which is, okay, let's find OBS SUSE, the open build system. That it's the platform where you can build kernel module packages, KMPs, for SUSE. SUSE requires to use this build service in order to certify the creation of the KMPs. In the playlist of this series of recordings, you're going to find a one-click process to build the kernel module, and I'm explaining in detail how to use the OBS system and the process of automating everything with Jenkins and OBS. So here I'm going to search for Navencrypt. I already had it over here. And if you see I'm not logged in, which is what I'm expecting, I don't have access to this anymore. So you're going to find the project name Alex Gonzalez, myself, and the Navencrypt Kernel Module, and this was created time ago. So when you go to the project of the OBS, you're going to see how many versions we're building for SUSE. In this case, it's less 11 SP2, SP3, 12 SP1, SP2, and SP3 and SP4. So it's pretty much all the versions that are still under maintenance from SUSE. And here you're going to find the project requires a specification file, and as well the tarball where the source code of Navencrypt sits. You cannot click here in this project, but you can find in the repositories. You can find, for example, I think if we go here, you can see the download repository. You can go to SRC, and here it is. Here it is the source file. So you can click, and it's gonna download. Let's do it. Yeah, it's coming here. It's coming here, and as I said, this is only the source code of the Navencrypt Kernel Module. So what I'm going to do is decrypt it, and then I'm going to give you a quick code walkthrough. Okay, I said decrypt it, but I meant to unzip it. Pretty much extract the source code from the RPM, which is going to stay in a tarball, and then the tarball it's untarbed. So yeah, this is the code of Navencrypt kernel module. I'm going to focus on the ACL, which is the access control list, the authorization file, and I'm going to talk about the hooks, which are the three main components. The rest of them are debug, are configuration, the KMS operations. You can see the main file. Some messaging that is not relevant, some profile that I'm going to talk when we go through the ACL, statistics, and general libraries. That's why I'm saying that I'm going to talk only about three files that are the most important for the Navencrypt kernel module. So it's very important that we look into the hooks file, because this is the interceptor of the read and write operations along another inode and superblock operations. So if you see the basic file operations are open, so we're gonna pretty much intercept the IO and do the call into the Navencrypt code, and after that we are gonna send the control to the next one in the stack, which is gonna be Navencrypt or eCryptFS. So it's the open operation, the read operation over a file, the write operation. All of them are going to be hooks that are overridden and then calls the next one in the stack. We have the IO read and the IO write over here as well. And then we have inode operations that it helps to locate the files inside of the directory and adds the new nodes into the inode list that CEncrypt controls, such as the operations lookup and create when we are doing the mkdir, mknode, CEncrypt link, symlink, And finally, the superblock operations that we need to have in order to destroy a node superblock operations once we're done with the Navencrypt. So the CNcrypt inode needs to be added to the inodes list or removed. So one of the superblock operations is destroy the inode, or to kill the superblock when the superblock from CNcrypt is not used anymore into the file system. So those are the basic operations that we're doing over the hooks. Yeah. Now let's move into the ACL file. Okay, so the ACL file is the access control list file, and this one is the main author of Navencrypt Kernel Module, Sergio Peña, and I am one of the contributors. Here, as mentioned in the architecture, we have a list, a process list, which is the one that is going to contain the list of a load or whitelisted processes. So we're going to initialize it or free when we're not using it anymore, or we're going to add the process to the list when it was authenticated, or we are going to remove it from the cache list, which is the one that is the one that is handy to prove that the process is still there. And since we are allowing processes, what we're doing is getting the process signature, meaning that we have the checksum of the process, and that's the value that it's added to the list. That's why in this case we're freeing the process, the ACL from the free process signatures list. And as well, there is an ACL operation where we are going to add rules or we are going to remove rules. And the rule is going to have the process fingerprint, the category that it's being allowed to access to, and the access, which is allow or deny. Basically, everything is blocked until it's allowed, which means that the list is going to contain only the processes that are allowed. You can add explicit rules to deny, but those are by default anyway active. Yeah, more operations with the some particular operations with the shell needs to be performed for the shell process. It needs because it's being bash usually or being dash, and it needs special treatment. So we need to create free process mechanisms or algorithms specific for bash and dash. One of the important things that is a Navencrypt kernel module working with is profiles. Java is a process, and you cannot allow Java to access anything because anyone can write any Java program and have access to your data, and you're going to be hacked. So the thing is that we created a process or a profile for the process and the Java, and it's based on the parameters of the Java application, and the gathering of those parameters to the Java application, it's going to become a profile. The profile as well has a fingerprint, so it has a special treatment. We need to initialize the list of the access control list. We can clear it, as mentioned here. We can release the entire list. We can search the process per fingerprint or signature. We can add a process by signature, as well as I mentioned, the shell. We can add a rule to the access control list. We can We can load the rule from the keyring because the way that the user space and the kernel space communicates through the buffer named keyring. So that's where we are sending all the parameters that are required in order to add an ACL. We can load the process signature from the keyring as well. We can load the process shell from the keyring as well. We can load the profile, the Java profile, all the parameters that are fingerprinted, as I mentioned, from the keyring. And those are the basic operations that we can have with the ACL. Now, this is just to create or to do operations with the access control. It's saying what processes are going to get the fingerprint, where the fingerprint is going to come from. Maybe it's going to come from the keyring, and when we can add an ACL rule or remove an ACL rule. But the real authentication operations are done on the auth.c file. So we can read the crypt key from the keyring or the encryption key that is sent from the user space, and it's stored in the key trusty server, and it's necessary to pass it to the next one in the stack to perform the encryption, which is going to be cryptfs or dmcrypt. We can verify if a process is authenticated, and it's on the cache of the processes that are allowed. We have a global authorization key to perform the pass of the buffer from the keyring that is named Navencrypt key. We can read the content from the keyring, whatever that is. We can read the fingerprint of the shell or the profile, etc. Some utility operations such as trim. And we can read the process file path name in order to get the content read from this function that is going to perform the checksum or the fingerprint of or signature, has different names, of the process. Here we can get the process file. Not the path, but the file name, the path name. We have the process information stored in the cache. We can free it. I don't recall this one. This is gonna print only the process information. It's just a print message when you are debugging or adding some traces. You can get the file descriptor of the process shell. You can get the process script file. This is important because in a couple of seconds you're going to see another functions that are going to be doing the case where you have a bash file, for example, or script that might be updated and it changed. And if it changed, probably it was by a malicious user, which means that it's vulnerable now and the fingerprint of that has changed, so the authentication has to fail because the original script that it was allowed changed, right? We need to update the rule with the new fingerprint, and you need, of course, a master key. This is only printing information. This is going to see if the process is authenticated. As I mentioned, if the process is not authenticated by the fingerprint, then the authorization is going to fail and the access is going to be denied. And this is one of the challenges I mentioned before in regards to Navigator Encrypt. Some specific cases we need to add them for a specific kernel version based on their kernel improvements and the way that the structures are declared. So sometimes we need to use different types of calls to get the proper API, kernel API, in order to use it with Navigator Encrypt for a specific version. This digest is the fingerprint, and we are using SHA-256 to do the fingerprint, and this one is going to check the 5 checksum, which is the fingerprint of the file, to see if this is an allowed process or not to access encrypted data. Navencrypt calculates the string checksum, and the string usually comes for the profile, which is the parameters of a Java process. This is going to read the process signature. This is going to save the process on cache. Once it's authenticated, then it goes into the cache to know that it's there. And this is going to alert that the process has changed. If the process has changed, we need to say that it's going to be denied. The access is going to be denied, right? And this is the authentication process of the process, of course. This is only verify if the process is assigned to the rule. If it is, then it means that it has access to whatever is in the rule, and the authentication succeeds. It gets access gets the access category, which means that from a rule we are going to see the category, and the process is going to be matched with the rule in order to see if it has access to a category. Some processes have childs such as bash files. Bash files have a call to another process that is a bash as well, or maybe a Java application, or maybe another process. So it's taken into account when you have the authorization of the childs to access. So you need to have multiple rules to do that. This is only for rules comparison to see if it's not a repeated rule. You can get the access type, as I mentioned before. You can allow or you can deny the access of a process. By default, everything is denied, and everything that's allowed is whitelisted. You can get the access permission, which is going to be allow or deny. And you can verify access control. It's just a process to see if the process has access to the encrypted data, and this is kind of the master function that is going to control everything. So this is the walkthrough of Navigator Encrypt Kernel Module in some simple words. And any questions you might have, please contact me on my Twitter account, which is KOZLEX, Gonzalez. Thanks so much.